All right, so the next little topic we're going to cover is mechanisms of reactions, and we're going to do an example of a particular type of step. It's called unimolecular. That means it involves one molecule, just like a unicycle has one wheel. And I'm going to say reaction steps. So any chemical reaction happens in a series of one or many steps. So an individual step is actually, when you write the chemical reaction down, that's actually what happens. So the example we're going to use is something called 2-butene. And 2-butene, first of all, the BUT is the root word for butane, which has 4 carbon atoms. And an alkene is a organic compound with a double bond. And so there's 2 carbons here in the middle that have a double bond. All right, and so I'm going to write this in shorthand as that. Okay, so it's very important for actually just to understand some of the language used in society nowadays. If the 2 carbons are on the same side of the double bond, this is called cis. All right? And cis is kind of like same side. And the other way we could have drawn this compound is called trans. All right, and of course, trans is all in the news in 2016 for various reasons. And so actually people talk about transgender and cisgender now. And it's all based on the chemistry of organic compounds, particularly the double bond. Now the double bond in these compounds is more or less rigid. That is to say that cis will not change to trans unless the reaction conditions are correct. But generally speaking, if you have a molecule substance that's got cis bonds in it, they will stay cis until they go bad, actually. Okay, so an example of cis organic compounds are called fatty acids. And fatty acids are hooked together into triglycerides or oils or fats. It turns out that in order to get an oil, you need double bonds. And those compounds, since there's actually a difference between a carbon-carbon double bond and a carbon-carbon single bond, you can have 4 single bonds to carbon. So if you were actually take a chemical reaction and add H2, you can get this compound. Where the carbon in the middle has a single bond. And now it can freely rotate. And so that's key to actually some of the chemical processes that convert cis to trans. All right, and so these 2 combine to form that. And so this is a process called hydrogenation. Okay, so these tend to be oils or liquids. These tend to be solids. So we call fats that are solid fat. And so things like bacon fat, lard, Crisco, and that sort of thing. These are oils like olive oil and soybean oil and all those. Now it turns out that these are more or less, they react with air, so they go bad a lot faster than saturated fats. And also saturated fats tend to be more solid, and so in baked goods, they don't spread out. And so if you ever make cookies with oil, they'll spread out, whereas if you make cookies with a solid fat like butter, then they will keep their shape a whole lot better. Of course, they taste great with butter. All right, so the thing about this process, though, is it's actually reversible. And so you can take a cis oil, like olive oil, try to hydrogenate it, And then if the hydrogens go back off after it's flipped to trans, then you can get some unsaturated fats that are trans. So this is where trans fats actually come from in your foods. They start off with cis, they try to hydrogenate. It doesn't happen completely. Some of the molecules, they rotate their single bonds while the hydrogen's on, and if the hydrogen comes back off, they could be stuck at trans or cis. So that's how you get trans fats. So let's talk about the actual mechanism of conversion of cis to trans. Okay, we're not going to talk about the chemical reaction. We're just going to talk about actually what happens, what is required to twist this molecule. All right, so let's look at it from the side. Okay, so when you look at the geometry, CH3, there are 3 groups of electrons. So this carbon here, sp2. This carbon here is sp3, just to review your general chemistry. And so the skeleton has 3 bonds, 3 groups of electrons. That's how you know it's sp2 hybridized, because the number of sigma bonds is equal to the number of atomic orbitals that hybridize to form the sigma bonds. All right, and so now there is the remaining p orbital, and we'll call that a pi bond. Okay, and so a pi bond is an overlap of 2 p orbitals like that. Okay, so the molecule is flat and the p orbitals are above and below the plane of the molecule. So if the molecule is in the plane of the screen here, the p orbitals are coming out at me and out at you. So what we did was we rotated so that now if the molecule is this way, then the p orbital is above and below. And so the overlap of the p orbitals form a pi bond. All right, so now next thing to do is envision what happens to this bond as we twist the angle. We'll call the angle phi. All right, so now the angle between this carbon and this carbon, so now we're going to have to actually draw it in another orientation, looking at from the end. And the best thing for me to do is illustrate this. All right, so imagine my fists are the methyl groups, my elbows are these 2 carbons. And so cis means my fists are on the same side of the carbon-carbon bond, which is my elbow to elbow. All right, and so if I look at it from the side, you can now see that the angle between this bond, this CC bond, and this one is 0 degrees. If I twist this, it's now 90 degrees. Now it's 180 degrees. That's trans. So between cis at 0 degrees and trans at 180 degrees is probably a place at 90 degrees where there is no pi bond at all, because as you twist these 2 molecules, the amount of overlap between these 2 lobes gets smaller and smaller, and of course it goes to 0 when it's at 90 degrees. But then when you keep going past 90 degrees, then all of a sudden the bond forms again. Okay, and so at 0 degrees and 180 degrees, you have stable structures. That is to say, it's the lowest energy that they can have in that vicinity. So these molecules tend to, if you try to twist them, will try to snap back. And so what happens is, you know, they're in a collection of all sorts of other molecules, kind of like in a mosh pit. So unimolecular reaction steps, there is energy coming into the reaction, but it doesn't depend on what's hitting it. It's just a matter of something's hitting it and starts knocking it around. And eventually it'll get enough energy to flip. Okay, so if you knock it hard enough to get it to 90 degrees, then it can go past and down the other side. And so this particular geometry at 90 degrees, it's not exactly 90 degrees, but it's very close, would be something like this. So the two carbons in the middle are kind of like obscuring each other. And actually in something called a Newman projection, we could actually say what the front one is. In the Newman projection, the front one is drawn to the very middle of the circle, and so that would be the carbon that's closest to you. For example, this one would, and then the back one, of course, you can't see all the way to the middle of the back one because it's being hidden by this guy, so you'd only see the line to that point. Okay, so let me just draw the Newman projection colors in different colors. So the CH3 bond would only be drawn to here, then the rest of it's hidden. This one here is not hidden because it's in front, and so you see it like that. And so this angle, 90 degrees, is what's being plotted here. So that's the molecular structure of this thing. This is cis and this is trans. Now, cis and trans actually don't have the same energy. It turns out that trans double bonds are slightly more stable than cis. It's not much, but it is enough so that this is the most stable form. Okay, now the energy required to go from cis up to enough to go over this mountain, so this is called an activation energy. So this energy difference is called EA, the activation energy. Now, once you get over this amount of energy, so basically once you have enough energy to get it to 90 and it goes on, then it's still getting knocked around. It can still maybe flip back to cis. And so what you'll see is an equilibrium between, these molecules, and then when you look at any one particular molecule, it'll be cis some of the time, it'll be trans some of the time. And so what you look at is the composition over time. It'll reach a point where the number of each is kind of more or less not changing. So EA prime, of course, is the mountain height for coming back. Of course, if you could go over to Homewood, the height of the red mountain between us is different depending on which valley you're coming out of. All right, so that's an example of a unimolecular reaction step. The important thing to realize is that the rate of reaction is, since it's a single step, the forward rate Okay, so it turns out in this example, there's an equilibrium between the cis's and the transes. Okay, so they're constantly converting one back to the other. So not only is cis going to trans, but trans is going back to cis. So what we like to do is actually write the chemical reaction just one way, even though it's going both ways. And so we draw for the reverse reaction the backwards arrow. So the forward is rate equals a constant times this to the first power. So if you have a single step, the stoichiometric coefficient 1 is the power here. All right, so for the reverse reaction, since it's one trans converting to one cis, it doesn't matter what the product is. Since there's one trans, the rate of the reverse reaction, which I'll call rate R, depends on the number of transes. Okay, so it's a real simple sort of concept. If you have no cis molecules, you can't have any of them being converted to anything else. Okay, if you have no transes, you can't have any of them being converted to anything else because there are none. All right, and so and what this expression says, it depends on the amount to the linear power. So if you have, if you double the amount of cis molecules, then all of a sudden you're going to be doubling the rate at which they convert to trans. If you double the amount of transes, you automatically double the rate at which they convert from trans back to cis. Okay, so in the next chapter, we're going to introduce an idea called chemical equilibrium, where the rates are equal. Okay, so if you wait a long enough time, the rates will eventually become equal. That means the forward rate equals the reverse rate. And but if the rates are equal, that does not mean the Ks have to be equal or the concentrations. It's the product of the constant times the concentration that has to be equal for forward and reverse. And so in general, the rate constant is not the same. As a matter of fact, the rate constant is related to the barrier height. Okay, so for a large activation energy, you get a small rate constant. Okay, so the higher the hill, the more energy is required to twist the molecule, the less frequent that a collision is going to impart that energy required to get over the activation energy. All right, so since trans has the higher hill to get over, then the trans rate constant for the reverse reaction from trans back to cis, this number will be larger than that number. Okay? So, sorry, this number will be smaller than this number. Since this number is smaller than this number, in order for the products to be equal, this number has to be larger than that number. Okay, so if we have an equilibrium established, and the more stable product will actually have more molecules. All right, so since trans is the lower energy of the cis and the trans forms, we expect the trans molecule to be dominant in the equilibrium. Although in reality, they're very close in energy, so they're very close to 1-to-1 ratio, maybe 50% more trans than cis. Okay, well, that's it for unimolecular.